US Physics Olympiad, year 2014, USAPHO. Final exam. Problem A3. When studying problems in special relativity, it is often the invariant distance ds between two events that is most important, where ds is defined by this equation, where c equal 3 by 10 power 8 meters per second is the speed of light. Question A. Consider the motion of a projectile launched with the initial speed v0 at angle of theta 0 above the horizontal. Assume that g, the acceleration of free fall, is constant for the motion of the projectile. First, derive an expression for the invariant distance of the projectile as a function of time t as measured from the launch, assuming that it is launched at time t equals 0. Express your answer as a function of any or all of theta 0, v0, c, g, and t. Question 2. The radius of curvature of an object's trajectory can be estimated by assuming that the trajectory is a part of a circle. Determine the distance between the end points and measuring the maximum height above the straight line that connects the endpoints. Assuming that we mean invariant distance as defined above, find the radius of curvature of the projectile's trajectory as a function of any or all of theta 0, v0, c, g. Assume that the projectile lands at the same level from which it was launched, and assume that the motion is not relativistic, so v0 much less than c, and you can neglect terms with v over c compared to terms without. Solution. In our case, we have for delta t equal t, delta x equal v0 cosine theta 0 t, dy equal v0 sine theta 0 t minus 1/2 g t square. When we put these meanings to our expression for events, we have s square equal this one, or after simplification, this one. That's the answer for question I. Solution for question 2. In time-space frame of reference, we have for v much less than the speed of light, invariant distance approximately equal this expression, and we can find what is total time by using this equation. So it means that invariant distance for time t will be this one. And now we can find what is the height in this time space. That's a z. Maximum height will be this expression. And now we can find what is approximate curvature of this curve. Suppose that this is the graph of our trajectory in time-space coordinates s and z. In that case, AB will be distance this one, and z, that's a height this one. And now we can find what is the radius of this curve. We can find it from such equations. We have s approximately equal radius multiplied by small angle theta, where theta is not theta 0. That's a different one. And also we can find what is z. So we have maximum height approximately equal this expression, which is r theta square over 8. And now from these two expressions we can eliminate theta, and from here we can find what the radius is approximately this one, or c squared over g. That's the answer for question 2. Part B. A rocket ship far from any gravitational mass is accelerating in the positive x direction at a constant rate g, as measured by someone inside the ship. Spaceman Fred, at the right end of the rocket, aims a laser pointer toward an alien at the left end of the rocket. The two are separated by a distance d, such that dg much less than c squared. You can safely ignore terms of the form of this one. First question. Sketch a graph of the motion of both Fred and the alien on the space-time diagram provided in the answer sheet. The graph is not meant to be drawn to scale. Note that the t and x are reversed from a traditional graph. Assume that the rocket has velocity v equals 0 at time t0 and is located at position x equals 0. Clearly indicate any asymptotes and slopes of the asymptotes. Second question. If the frequency of the laser pointer as measured by Fred is f1, determine the frequency of the laser pointer as observed by the alien. It is reasonable to assume that f1 much greater than c over d. Solution. Here we have a graph ct as a function of x, and because spaceship is moving with acceleration g, in regular case we have on axis y ct is linear to time, and on graph x is quadratic to time. So it means that in regular case we have to make a reverse parabola. But because speed cannot exceed speed of light, we have slope of each curve must go to this asymptote, and finally got very close to it. And the question is, what is the distance between alien and Fred finally? Because in moving frame of reference the distance became shorter. It means that these two curves, they have same asymptote, which has slope c, speed of light. And both trajectories looks like some kind of hyperbola. Basically, this is the answer for question 1. Question 2. If the frequency of the laser pointer as measured by Fred is f1, determine the frequency of the laser pointer as observed by the alien. It is reasonable to assume that f1 much greater than c over d. Solution. Let's draw the picture for this process. To solve this problem, we replace the light with a series of discrete flashes. Then find how the frequencies of these flashes are seen by Fred and the alien. Let Fred emit a flash of light at time t0 and the second flash of light at time t equal tau, where tau is very small. Let the alien see the flashes at time t1 and t2, which we showing on this diagram. Then by ordinary kinematic we can write equations. For the first flash we have for time t1 this equation. So it means that distance d was reduced by 1/2 g t1 square, and that's equal to c multiplied by t1. Here we have a distance covered by flash of light for time t2 minus tau. That's equal to position of thread after time tau, which is 1/2 g tau square plus d, minus position of alien at point t2, which is 1/2 g t2 square. So we have these two equations, and let's subtract from second equation first equation. So after that we have this equation, and now let's delta t be t2 minus t1. We have this equation, and because g tau over 2c it's very small, this approximately equal tau. And because g is very small, and we are looking only for the first order of g, we can say that t2 approximately equal t1 approximately equal d over c. And finally we have f alien over f thread equal tau over delta t, or approximately it's 1 plus gd over c square. That's the answer for question 2 in part B.